Hello and good day everyone, my name is Ron and let us answer some heat exchanger problems. Create a simple heat exchanger simulation in DWSim using the following parameters, where the cold stream is a toluene feed and the hot stream is an acetone feed. Using the property package Raoult's law, the cold inlet stream is purely toluene with a mass flow of 30,000 pounds per hour, temperature of 100 Fahrenheit, and pressure of 1 bar, while the hot inlet stream is 15,000 pounds per hour, pure acetone, temperature is 200 Fahrenheit, and the pressure is 5 bar. Assuming that the flow is countercurrent and the overall heat transfer coefficient is 270 watts per meter squared per Kelvin, and the heat exchanger area is 75 meters squared, with the cold fluid pressure drop being 0.0035 bar and hot fluid pressure drop being 0.0025 bar, what is the resulting outlet temperatures and how much energy was transferred? So, I will represent the problem using the diagram shown. So, it is a countercurrent flow, meaning that hot acetone moves from left to right and cold toluene moves from right to left. Doing a countercurrent flow, we are able to simulate it using DWSim and show its legitimacy using hand calculations that I did so myself. So to start, also noting the required and the energy transferred, let us start with the simulation. First is we need to create a new process model. And then we'll do the general procedure for DWSim. So after loading, we click next, and the following compounds are toluene. So we click here toluene and acetone. There you go. Next, the property package used is, according to the problem, Raoult's law. So here Raoult's law, add, next, and then a system of units we will match our system of units with a given problem. So the temperature used is Fahrenheit, and then the pressure used is bar. We'll also use the pressure drop as bar according to here. Pressure drop, pressure difference, bar. And then the mass flow rate is pounds per hour. So we hear pounds per hour. And then double check in the area is meters squared, area is meters squared. Heat exchanger coefficient, heat transfer coefficient is watts per meter squared per Kelvin, and we are ready. So click finish, and then we need to say it is stated that it is using a simple heat exchanger according to this problem. So that means that for simple heat exchangers, we need to go to the exchangers tab, click on heat exchanger, wait for it to load, and due to the quality of the new update of DWSim, all the streams are already automatically shown. So we will rename these as follows, given by our given problem. So we'll put here as hot acetone. And another entry is the cold toluene. And hot comes in contact with cold, it becomes cool. So we'll call here cool acetone. That's the outlet. And cold that comes in contact with hot becomes warm. So we'll call this warm toluene. And we need to specify our inlet conditions. So for the hot acetone, we have 15,000. We have first 200 Fahrenheit. And then 5 bar. And then 15,000 pounds per hour. Lastly, for the compounds, according to here, it is pure acetone. So put here 1 and put here 0 and click accept. Alright, so double check. Only pure acetone, so 1, 0, and then 15,000, 5 and 200. Good. Now for the cold toluene, it says here that it is 30,000 pounds per hour with a pressure of 1 bar. And a temperature of 100 degrees Fahrenheit. And going by the composition, it is only pure toluene. That means this is 1, this is 0. Click accept. And we need to specify, let's double check again to be sure. So 1 pure toluene. And then this is 1 bar, 30,000 pounds per hour, and 100 Fahrenheit. That's good. And then we need to specify our heat exchanger properties. So according to the problem, it is in a counter current configuration. we'll put here as counter current. Okay, that's already set. And what we want is the outlet temperature, so we'll just leave it as is. Then we need to specify the cold fluid pressure drop. So according to here, the cold fluid pressure drop, or the heat, or in this stop, is 0.0035 bar. So cold fluid pressure drop is 0.0035 bar, and then the hot fluid pressure drop is 0.0025 bar. Alright, and then the global heat transfer coefficient, which is 270 watts per meter squared per Kelvin. And lastly, the heat exchanging area is 75 meters squared. Heat loss to the environment we will assume as 0, meaning that the majority of heat transferred from the hot is transferred to the cold. No heat is escaping from the system. And we will click ignore LMTD error. And this is the result. So according to the simulator, the resulting outlet temperature for acetone is 109.914 Fahrenheit, while for the warm toluene, it's 161.096 Fahrenheit. And lastly, how much energy was transferred? So according to here, the energy transferred is 238.594 kilowatts, and the maximum heat exchange is 262.358 kilowatts. So, how would we compare this to our hand calculation? Well, doing a hand calculation without knowing both outlet temperatures requires an iterative solution. Therefore, I did it in an Excel sheet and summarized the results here in this Word file. So, how I started with the iterative solution, first I will need to find the bulk temperature of toluene. Why did I need to find the bulk temperature of toluene? Because I need to find the properties of toluene. However, there are different temperatures in and out. So how do we find the properties if there are different temperatures in and out? Well, we need to find the average between the two. And finding that average temperature, same thing with the acetone, we'll be able to calculate a good estimate of the stream's properties, such as heat capacity, viscosity, so on and so forth. But for this case, we only need the heat capacity. So after calculating the bulk temperature, however, we don't know the outlet temperatures yet. So we'll just leave it as is, as a formula. So we don't know the outlet temperature of toluene, which is T1T, and we'll just leave it as a variable. And then we need to find the heat capacity of toluene. However, this formula is obtained from Perry's Chemical Engineering Handbook, 9th edition, and this is originally in the units of joules per kilomole per Kelvin. However, we need to convert it into joules per pound per Kelvin in order to satisfy the units to be cancelled. So after doing certain conversions, we will have the following formula. We cannot solve it yet because we still do not know the bulk temperature of toluene, since the unknown temperature is the outlet of toluene. But we'll still continue. So using the heat capacity, and since we're already given the mass, we can now find the sensible heat of toluene, Q equals mc delta T. However, again, we don't know the outlet of the toluene, so we'll leave it as an equation. And we'll convert it, since the mass is in pounds per hour, we need to convert it into pounds per second, or in a per second time unit, since joules per second is equating to watts. So that's why there's a dividing by 3,600 seconds. Lastly, we need to find the log mean temperature difference. The log mean temperature difference is related to the overall heat transferred using the following formula based on the energy heat coefficient and the heat transfer area. So using this formula and using algebra, I'll be able to isolate this equation. And lastly, finding the outlet temperature, since we already know that the LMTD method gives us a value after substituting this equation, we'll be able to find the outlet temperature by knowing the definition of the LMTD, which is the change of temperature in the exit minus the entrance over the ln of the exit over the entrance. But for countercurrent case, instead of exit and entrance, since both exit and entered at each side, we'll say that left and right. So that's why we have here left minus right, ln over left minus right, ln over left and right. So substituting the variables based on the diagram, and we would have this equation. Then, after assuming that we already know T1T, and we calculated LMTD, we're able to find the other outlet temperature of the other stream, T2A. So, if we assume that we have T2A, we can now find the bulk temperature of acetone using the same algorithm, and then we still find we need to find the heat capacity of acetone using the bulk temperature of acetone calculated earlier, and we would have this equation after undergoing certain unit conversions respectively. And then in order to find the new calculated outlet temperature of toluene, or T1T, we need to do a heat and energy balance. So doing a heat and energy balance means trying to sum all heat in and heat out. Normally, heat and energy balance uses enthalpy, mass times enthalpy. However, in this case, we will assume that enthalpy, or H, equals Cp delta T, and the change in enthalpy is simply equal to Cp delta T. That's an assumption we would use, a simplified assumption to be able to truly quantify the system itself and simplify also. So if we assume that the change in enthalpy, this is essentially the change in enthalpy, is equal to Cp, or heat capacity of the system, times delta T, or change in temperature, hence why this is their form. Then doing some algebra, isolating T1T, which is the one we guessed earlier, this is our final equation. Now, the reason why it's iterative, because we guess the first value of T1T, then undergo the following procedure until we get to a new calculated value of T1T, and then equate that new value back to the original value and repeat the process again until we create a convergence of values. So this is the step-by-step procedure. So I would guess any value of T1T, then using equation 1, I would find TBT. Using equation 2, I would find heat capacity. First, the bulk temperature and heat capacity. Equation 3, I would find the heat transferred. Equation 4, I would find the LMTD. Equation 5, I would plot the LMTD equation in Desmos and try to find T2A, or the outlet temperature of acetone. Then I would find the bulk temperature of acetone using equation 6, the heat capacity of acetone using equation 7, the new T1T using equation 8, and equate T1T to the guess and repeat back to step 1 and repeat until convergence is observed. So, this is the tabulated summary of iterative solution. By the way, you might be wondering, why is it that in number 6, in the 6th step, it's quite unique compared to the other descriptions? It's because in the LMTD, if you're going to do shift solve, it might be a bit hard to do. It's because sometimes the calculator will not give a value due to some convergence errors. That's why what I suggest is to plot this equation, given that you already guessed an initial value of T1T, and you're trying to find T2A, but you already found delta TLM, or LMTD. You will be able to find the corresponding T2A if you plot this as y equals the following equation, where you put T2A as x. And that's how you can get an easier way, that's an easier time to get the LMTD, DT2A method, using the LMTD calculated earlier. And this table summarizes the iterative solution that I've done in Excel. So I initially guessed a outlet temperature of toluene as 500 Kelvin, then substituted it in equation 1, then equation 2, equation 3, and equation 4. And I remember earlier that I said that plot the equation for LMTD in order to find T2A. So what I did is this one. So going to Desmos, this is the equation I prepared earlier. And A represents the guessed T1T, which is 500. So I'll put here 500. And then, when I scroll up, I would get this graph. Then knowing the LMTD, I would need to find the LMTD that corresponds to that said graph. So going to the LMTD, knowing that the LMTD is 73.79, and since it's just a change, LMTD, the y can also be in negative form. The important thing is that you need to find the x-axis that corresponds to the y LMTD, regardless if it is negative or positive, since it's just a change value. So 73.79 is around 73.79 is at around 275.6. So here, that's how I got it used graphically. Then the Excel will continue on until T1T, and then still continues on automatically Excel, and then a new LMTD method with corresponding to a new T1T. So let's do it again. So 359.84 oh sorry, 359.84, and then also here 359.84, and this is a new graph, and I need to find the graph that corresponds to a y value of 16.57. So going here, 16 point, scroll, magnifying, 16.57, it is around 344.3 or 344.35. That's a more exact point. And this is the algorithm that I just kept repeating until I get the ninth iteration, where the values are almost essentially similar to one another. Hence, I concluded that they are at convergence. So, the convergence values using the iteration table are as follows. The outlet temperature of acetone is 315.38 Kelvin or 108.014 Fahrenheit. The outlet temperature of toluene is 244.26 Kelvin or 159.998 Fahrenheit. And lastly, the total heat transferred, assuming that no heat is escaping from the system or no heat is wasted to the environment, is that it is 224,490.78 watts or 224.491 kilowatts. Then, the product of DWSIM are as follows. Let's double check. The acetone is 109.914 Fahrenheit. The outlet toluene is 161.096. And then the heat transfer, heat exchange. We will not use the maximum heat exchange. We will only use the heat exchange, the actual heat exchange. So the actual heat exchange is 238.594 kilowatts. 238.594 kilowatts. Then, we just need to determine their percent difference. So doing a percent difference for toluene, we would have a percent difference of 0.68, very, very low, which is good because that means they're very, very similar in terms of how they were acquired. Next is the percent difference for the outlet acetone temperature of T2A. So it is also very, very low, below 5%. So this is a good premise. And lastly, the percent difference of energy transferred is around 6.09%. Though it's above 5%, it is still an acceptable value in terms of difference. So, my conclusion is that the comparison between handheld calculations and simulation shows similar results. A possibility of its slight variation, meaning that why is it not exactly 0%, why is there a slight difference, is that the simplified method that I used in this calculation is compared to the rigorous calculations done by the simulator. Meaning that I was not able to truly identify or to truly use the Route's law property package here, because I don't think during the production of this algorithm there is no application of the Route's law equation. If you want to know what I'm talking about, please refer to my videos in Let's Solve separation processes, where Route's law is more used and explained in that video. But for this video, heat exchanging, this algorithm is as follows. This algorithm follows in the book of June Copley's, and there is no use of the Route's law property package here, specifically in hand calculations wise. So that's why the slight variation may be a result or a consequence of not using the Route's law property package in terms of hand calculations. Another reason why there's a slight variation might be in terms of the rigorousness of the calculations, because remember that I assumed for the heat balance here, the heat balance normally it's truly enthalpy. However, I assumed it to be Cp delta T, meaning that heat capacity is simplified. However, normally in real systems, this equation is not really applicable because this is assumed in an ideal case. So that's why maybe the reason for its slight variation it's because, again, what I did in the hand calculations is simplified and easy to understand for lecture's sake, but for the simulator it's more rigorous and more calculative. But overall, as you can see, results show that the difference between hand calculations and simulations are very, very small, and we can expect that we can estimate a good value using the same method and the simulator as well. So again, my name is Ron. Thank you for listening, and I'll talk to you all later.